Our next section is 11.5, matrices and matrix operations. So first, let's talk about what a matrix is. Matrix is the singular form of matrices, which is the plural form. So a matrix is a rectangular array of numbers. So notice that all of these A sub 1, 1, A sub 1, 2, A sub 1, 3, these represent some number in its place. So they're not variables, they just are representing the location of each number, the corresponding entry. All right, so you notice that what this means is that A11, A12, A13, the 1, the first digit there represents which row the number is in. The second number represents the column that it's in. So in this case, we have M rows and N columns. It makes this guy, we call it an M by N. Those are its dimensions. Dimensions. Kind of like length times width, kind of a concept. So we have, for our M, those would be our rows, and N would be our columns. All right, so if we have two matrices, let's just go ahead and start with an example. Very often we will see them labeled as capital letters. So let's just say matrix A is 2, 0, 4, -3. Matrix B is going to be -4, 6, 2, 0. So let's note first that this one is a 2 by 2, meaning 2 rows and 2 columns. This one is a 2 by 2. All right, so we can add and subtract two matrices. So if we were to do A plus B, this is about as easy as it gets. We are going to add each corresponding entry. So the first two entries, 2 and -4, oops, I went with the wrong color there, that's all right, is -2. The second two entries, if I'm going to down the bottom left corner, 0 and 2 make 2. Then top right, 4 and 6, we're adding these two together, make 10. And then the bottom right hand corner, wrong color again, is -3 and 0. That will give us -3. So adding two matrices is as easy as it sounds. Subtracting is exactly the same way. If I were to do A minus B, we are just going to subtract each corresponding entry. So you should get, so again, we're doing 2 minus -4. So that makes 2 plus 4. So that's going to give us 6, -2, -2, and -3 when we subtract each corresponding entry. We can also multiply by a scalar. So let's just say we had matrix A and we want to multiply by 2. 2 times matrix A. This is very much like the distributive property. We're just going to distribute that 2 to every single entry. We're going to multiply every entry by 2. So the first entry, 2 times that 2 is 4. 4 times that 2 is 8. 0 times that 2 is 0. -3 times that 2 is -6. So that is multiplying through by a scalar. So just a few properties that we would like to point out. The commutative property of of addition, let's just say of addition, of matrix operations holds true. So that means that A plus B is going to be the same as B plus A. The associative property of addition, meaning if I had the quantity of A plus B plus C, is going to be the same as A plus the quantity of B plus C. And then the distributive when it comes to scalars, so distributive. So let's say I had, so I'm going to put a little c and a little d representing scalars. Let's specify those. These are scalars, just a number, not a matrix. So if I had two constants, C plus D times A, that's the same thing as C times A plus D times A. A is the matrix here. Or let's just say we could also, another form of the distributive would be, let's say I had little c, again a scalar, I'll point that one down here, little c, times, let's say we had A plus B. Well, I could also distribute that and say C times A plus little c times B, trying to make those littles, the lowercase, real obvious. All right, so those are the properties that hold true. Notice that there is no multiplication in these properties, and that's very important to note. We'll do multiplication in a minute. So let's look real quick at a matrix equation. Let's say I had the equation 2x, some unknown matrix, minus A is equal to B. So x is an unknown matrix. Well, and let's also define our A and our B. A we're going to define as 2, negative 5, 3, 1. B we will define as 4, 1, negative 1, 3. All right, if I was wanting to solve for this X unknown matrix, I actually can use these properties right here. So I'm solving for X. I want to know what X would be. Well, I know that I can add the A to the other side. So I have 2x is equal to A plus B. I can divide by 2 or multiply by 1/2 because I have distributive. So x would be 1/2 of A plus B. It's the same as dividing by 2. I could distribute if I want, or I could add either one based on the property here. If I add A and B first and then multiply by 1/2, let's see what happens then. A plus B should give me 6, negative 4, 2, 4. And then when I multiply by 1/2 by the scalar, each singular entry, 3, negative 2, 1, and 2 should be what. All right, so let's continue with multiplication. So this is the more complicated concept in this section, multiplication of matrices. So let's start with AB. Well, okay, before I do an example, let me explain something about multiplication, and I'll show you why. If A is an M by N matrix, B is an N by K matrix. So we are multiplying AB, so M by N, times, I'm going to use a dot here because I'm using X for my dimensions, N by K. So in order to multiply two matrices, the columns of the first and the rows of the second have to be the same. And I will show you why in a minute. But these two have to be the same. This is why the commutative property for multiplication does not hold true. Because notice, if I swap this around, if I AB, let's just say I wanted to swap and say BA. B is N by K, and A is M by N. Notice that my columns and my rows do not match, so that's why the commutative property of multiplication does not hold true. So for these two to multiply, the inner dimensions have to match, and the result will be the outer dimensions. So this will be an M by K matrix. So let me just show you an example first. Let's start out with A is equal to, we're going to call it 1, 2, 3, 4, 5, 6. Very creative. If we were in class, I'd ask you, what are the dimensions of this guy? You would say he's a 2 by 3. All right, then we're going to multiply by B. B, I'm going to make 7, 8, 9, 10, 11, 12. All right, I chose these numbers for a reason so that every number was distinct, and when you went home, you know, if I was doing this in class, that you wouldn't question where I got each entry from. So this guy, I'd ask you, what is his dimensions? What's B's dimension? And you would hopefully say he's a 3 by 2. So I would ask you, can A, B be multiplied? And you would say the inner dimensions do match, so yes, indeed they can. Then I would ask you, what will be my result? What dimensions will be the result? And you would hopefully say they will be 2 by 2. So my result should be 2 by 2. All right, so the way we multiply is essentially what's called a dot product of each row and column. So we're going to do AB is going to be, so we start with the first row times the first column. So in this case, that's going to be my top left entry here. So I'm going to say 1 times 7 plus 2 times 9 plus 3 times 11. So notice the 1 times the 7 plus the 2 times the 9 plus the 3 times the 11. First row multiplied and added with the first column. That's my first top left entry. All right, my bottom left entry, remember it's going to be a 2 by 2, so I'm only going to have 4 entries total. My bottom left entry will be the bottom and the left. So notice the top left is the top and the left, the top and the left. The bottom left entry is the bottom and the left. Again, same dot product. So 4 times 7 plus 5 times 9 plus 6 times 11. I hope you're catching the pattern here. So then we're going to go to the top right entry, the top right entry. So we're going to go with top row, right column, dot product. 1 times 8 plus 2 times 10 plus 3 times 12. And then we're going to do the bottom right entry. So hopefully you've guessed by now it's going to be bottom and right. So we're going to say 4 times 8 plus 5 times 10 plus 6 times 12. This is going to be the product of A times B. I came up with, hopefully I don't have a mistake here, I came up with 58, 139, 64, 154. That will be the product of A times B.